In this lecture, we are now going to talk about Miller indices of planes. So, again let us take a few examples to understand this. Again, I am taking an arbitrary unit cell. Do not go by the shape of this unit cell that this is a cube. It can be a rhombohedral, it could belong to that orthorhombic unit cell, triclinic, anything. So, first let us again begin with something simple. Again I need to specify, sometimes I can specify my unit cell vectors A, B and C like this as well. So, here let us take a plane. So, I am always going to take a plane which is completely inside the unit cell, though in that infinite lattice the plane will also extend to infinity. So, let us take a plane which has been drawn by joining the three corners of the unit cell. Now, in this what do I do? So, in order to define a plane even mathematically, we need to get its intercept or the points at which it intersects with the three axes A, B and C. So, here we can clearly see, again we are going to use fractional coordinates. The intercepts with the axes, very clearly see, along A it intercepts at 1, along B it intercepts at 1 and along C it intercepts at 1. So, this is the first step we need to get to the three indices for a plane. The second step, take reciprocals of the indices, which means in this case it is 1 upon 1, 1 upon 1, 1 upon 1, which is nothing but again basically 1 comma 1 comma 1. And the Miller indices then for this plane is 1 1 1, and notice this time we are putting these indices in circular brackets and not in square brackets. So, this is important that circular brackets are to be used conventionally to indicate that these indices indicates that we are talking about a plane. Let us take another example. So, this time we have joined three other corners of the unit cell. Again, what are the intercepts? So, now first of all, before I write down the intercepts, we should see that we have to change the origin in this case. We need to shift the origin here. So, by shifting the origin here, I can get the intersections with the axes A, B and C. So, in fact basically what I have done is my axes are drawn from here. So, this is A, this is B and this is C. So, this time if I notice my intersection, the plane intersects the A axis at this point. Basically it intersects at -1, it intersects the B axis again at -1 and it intersects the C axis at 1. Take reciprocals. So, basically reciprocals would be also -1 1, and then the Miller indices becomes, now again since I have a negative number I will put a bar on top. So, bar 1, bar 1, 1. Now, let us take a few more examples to understand this. In my first case, let us consider this plane. In fact, let me label it as well. So, A, B, C and D. So, this is basically one of the cube faces. So, what are the intercepts in this case? It intersects again, I have to show my axes. So, A, B and C. So, it intersects the A axis at 1. Where does it intersect the B axis? Well, it is parallel to the B axis. So, in fact, and two lines or two planes or line and a plane, if they are parallel to each other, we consider their intersection to be at infinity. So, intersects the B axis at infinity, intersects the C axis at infinity. And now we take reciprocals of this, which is 1 upon 1, 1 upon infinity, 1 upon infinity. And therefore, the numbers we will get is 1 and then 1 upon infinity is 0 and 1 upon infinity is 0. So, I will get 3 numbers 1 0 0. Now, you may understand the logic of why we are taking reciprocals, because we do not like infinity to be part of the Miller indices. So, my Miller indices simply becomes 1 0 0 for this plane. Similarly, if you will notice that if I have to get the Miller indices for this cube face, it is this time going to intersect with B axis at 1 and with the A axis and C axis at infinity, and hence the Miller indices for this would become 0 1 0. Similarly, if I take the top face, its Miller indices becomes 0 0 1. Now, consider another example where I will consider now a plane consider this plane, and let us say this intersects this edge AD at let us say half, it intersects the other edge at 2/3 and third it intersects at 1. So, therefore, the intersections with A, so again I shift my origin here. So, it is minus 2/3 along A, because this is my A axis, this is my B axis, it intersects the B axis at minus half, at it intersects the C axis at 1. Now, just like what I had done for directions, I want to remove these fractions and bring it down to integers. So, I can do this, but before I do this, I need to take reciprocals. So, reciprocals minus 3 by 2 minus 2 upon 1 and 1 upon 1. The third step would be the Miller indices. Now, I need to remove the fractions. So, there is only one fraction, the first one. So, therefore, all I need to do is I multiply by 2. If I multiply by 2, so I multiply everything by 2 and this gives me minus 3, minus 4 and 2, and therefore, the Miller indices becomes bar 3, bar 4 and 2. So, we have taken care of all possible cases that we can have. Now, we should be able to get the Miller indices for any plane we want quite easily. Now, I will take just this one example that I had taken earlier. Let us take this particular plane. and take this particular plane that I have already taken. I am just going to repeat it. So, the Miller indices for this plane we had obtained out here is bar 1, bar 1, 1. Now, suppose I negate all the numbers, then the Miller indices, this same plane can be represented by 1, 1, bar 1. Now, let us see how we could do this. In the sense, here in order to get these Miller indices, this was the origin I had taken. Now, let us do a small construction. I draw another unit cell just below it. And extend this plane. See, if I extend this plane, so if I just label these planes, it will be easier. So, let us say that this plane was A, B and C, and by extending it, I go to the point D. So, now basically it is the same plane continuing in the second unit cell or the bottom unit cell. So, let us now concentrate on the plane ABD and try to get the Miller indices for this. The Miller indices for this should represent the same plane as the Miller indices for the plane ABC. So, take the ABD. Now, where should I take the origin for this? The origin I will have to take out here. So, for this I need to take the origin here, and if I take the origin here, let us look at the intercepts. The intercepts along A it is 1, along B it is 1 and along C it is -1. Take the reciprocals and I will get 1, 1 same numbers, and then finally I will get the Miller indices as 1, 1, bar 1. So, we can see that 1, 1, bar 1 or bar 1, bar 1, 1 are representing the same plane. So, therefore, by negating the indices for the planes, I am basically representing the same plane. Now, finally, we need to understand one more thing regarding planes. Let us consider an arbitrary plane So, let us take a plane which intersects the A axis, B axis and C axis at some locations, and clearly what will be those locations? If this plane's indices were to be HKL, if the plane's indices were supposed to be HKL, then it will intersect the A axis at A by H. Remember, because we have to take the basically the reciprocal of the indices to get back to the intersection. Here it would be B by K, and along C it would be basically magnitude of C divided by L. So, I am writing the absolute intersections, not the fractional intersections. So, here the important thing that I am trying to focus on is that any plane HKL does not mean one plane. My lattice is infinite, it will be going to be a set of parallel planes. Now, where would be, let us say, the next parallel plane that will come? The next parallel plane that will come is if I take another distance of A by H. So, this will become 2A by H. Here this will become 2b by k and 2c by L, and draw a second plane. Since I have just travelled the same distance, basically this second plane is going to be first of all parallel, and it will have the same Miller indices as well. Suppose I consider the Miller indices for this. So, these are the actual intersections, 2a upon h, 2b upon k, 2c upon L. Take the reciprocals and remove a, b and c. So, after taking the reciprocals and go to fractional coordinate space only. So, this will become h upon 2, k upon 2, L upon 2, remove the fractional coordinates, multiply by 2, and I will get the indices HKL. So, whenever I say there is some plane HKL, I am actually talking about a set of parallel planes, and that is an infinite set. We can move in the positive direction, we can also move in the negative direction, which means there will also be a plane passing through the origin from which I had drawn the first plane, and then I can keep moving in the negative direction as well. Now, suppose I drop from this origin of, I drop a perpendicular onto the planes. So, this one maybe will intersect somewhere here, the first plane, the second plane it will intersect somewhere here, and so on, and you can imagine there is a third plane and a fourth plane, and one will see that the way I have drawn, the planes will be equidistant from each other. So, if let us say this is O, this is A, this is B, so we will see that OA would be equal to AB and so on. This distance between the planes, the perpendicular distance between the planes, is equal to what is called as the interplanar spacing, with the symbol I am using D HKL, which means this is the interplanar spacing of the HKL planes. We will see in a subsequent lecture that how we can calculate the interplanar spacing. Basically, we will get relationships, and these relationships are going to be different for different unit cells from the Bravais lattices. One final comment on the planes is, just like we had symmetry equivalent directions, we also have symmetry equivalent planes. To understand this, let us consider the cubic system. So, consider this plane whose Miller indices is 1 0 0. Consider this second plane, Miller indices is 0 1 0, and this top plane, the Miller indices is 0 0 1. And of course, once we consider this front plane, it is the plane at the back, which is the parallel plane, would also be part of the set of parallel planes. Now, these three planes, because, and suppose there are only lattice points at the corners, or even if you take the face centered cubic, you will see that all the planes would have the same set of lattice points at the corners, and if it is a primitive cell, if it is a face centered cubic cell, then one will see lattice points at the corners and the center of the face for each of these planes. So, all of these planes then can be clubbed together into a family of planes. In the case of directions, we have put angular brackets. In the case of planes, we are going to use curly brackets and we will write it as 1, 0, 0, representing all the planes, and we can write specific planes in circular brackets. And lot of times you will also see that the negative indices are also written. But otherwise, basically there are only 3 sets of planes. If I had, let us say, instead of this plane, suppose I had talked about this particular plane. Now, we have seen the Miller indices for that is 1, 1, 1. Family of planes, I will put it in curly brackets. And what are the families? I can write 1, 1, 1, I can write bar 1, 1, 1, I can write 1 bar 1, 1 and 1, 1 bar 1, and I also add, if I want, the negative indices, but they all represent the same set of planes. So, with this discussion on basically how to put indices for directions in planes is covered in this lecture and the previous lecture.